Start recording, Vivek? Yes. Please.
Okay, so hello everyone. So for those who I haven't met, I don't think it's many people. I'm currently a postdoc working with Alex Lopez. I did my PhD with her as well, but I'm doing a short postdoc at the moment. So I'm going to talk about two things today in this talk. So first, thermodynamics with carbon nanotubes. So it's going to be a bit exotic compared to what we've been talking about until now. And then the second topic is the energetic of pre-measurements. This is going to be much more in the line of what has been already discussed until now. So first, thermodynamics carbon nanotubes. So this is the work I've been doing in collaboration with the University of Oxford. So the experiments are done in the group of Natalia Ares in Oxford, with the experimenter being Federico Fedele, Kuchagra, Florian Vigneault, who has left some time ago already. So these are the experimenters for this experiment. And then on the theory side, I mean, we're working with Alexia. Juliette is also still involved in the project. There is Janet Anders from Exeter University in the UK. Federico Sarizola, who's working with Janet, and also Natalia. And Raspoli, who's helping us on the spin part of this presentation. And then we have also a collaboration with Juan Tarondo and Jorge Tabanera, who is a PhD student at the moment. So in this first part of the presentation, I'm going to present to you as a setup. So this carbon nanotube and what we can do with it. Then I will tell you about doing thermodynamics with charged qubits. Then if we want to go a little bit further, what can we do? So how can we, for instance, play a little bit with coherence? And to play with this, I mean, I will tell you about spin qubits with carbon nanotubes, which is something very new, still unpublished, that we're finishing at the moment. So here's the carbon nanotube setup. So the idea basically is that we have this carbon nanotube pair like that, which is above like gates here. So the carbon nanotube is our mechanical oscillator, so it's going to oscillate like that, up and down. And current can circulate in it. Not so well, but it can circulate. So in the middle, what we have is a quantum dot. So it's like basically a charge that is confined in some region by a confinement potential. And the confinement potential, it is generated via the gates that are below the carbon nanotube, while like we apply a different voltage to all of these gates to create the confinement potential for the quantum dot. And also through this gate, we are able to drive the mechanical motion, so to put it in motion like that. So what can we do with this setup? So basically what we have is this carbon nanotube. So what is nice, it has this mechanical frequency, has a good, I mean, not so good, but it has some quality factor, and it's oscillating like that. And we have on it this quantum dot. So first, at this moment, I'm only going to talk about charged quantum dots. So it means the quantum dot we are looking at is only, is there an excitation in the middle or is there not? This is our bit of information. So for the moment, at this stage, it's rather classical. So it has some bare energy that we can tune by varying the potential we apply on the electrons. This will change the energy of the quantum dot. And there is a quantum dot mechanical coupling that we will call G0. And then, of course, there are the reservoirs. So the left and right potential of like the source and drain electrode on the side. So as these things are coupled, there's this equation. So basically, when the carbon nanotube moves, I mean, there is some strength that depends on the population of the quantum dot. So if you have like an electron in the quantum dot, it will pull a little bit harder the carbon nanotubes towards the gate. So it will change a little bit the frequency of the oscillation. And also when the carbon nanotube oscillates, by its oscillation, it will change the potential that the quantum dot sees. So it will change a little bit the energy of the quantum dot. So this is how the two are coupled. And of course, there is the interaction with the observer. So now how does it work? So basically, a good way to model it is to say that, so we have some potential at the source, some potential at the drain. This is the carbon nanotube. So because the carbon nanotube is not a good conductor, I mean, effectively between this electrode and the quantum dot in the middle of the carbon nanotube, we will have this barrier, this general barrier. So, and same on the other side. And here what you have in the middle, it is a quantum dot with its energy levels. So what you can see here is that between the potential of the source and the potential of the drain, there is this bias here. And I mean, there are interesting situations that can happen. So for instance, if the energy of the quantum dot in the middle is not in between the source and the drain voltage, so it's not in the bias window, then at this moment, no current can circulate inside of the carbon nanotube. Whereas if it is indeed, like if we have an energy level that is in between the two, then an electron can jump in the carbon nanotube, well, in the quantum dot, and then jump in the drain. And we have some current flowing. So that's a way to have an idea of where, I mean, the level of the quantum dot is. So basically, if we look at the current versus the gate voltage, so the tension we apply around here, what we see is that are this column peak like that, in which you see that there is current at some point. So whenever you change this gate like that, up when the level is in between, you have a bit of current, then not, and then again at the next one. So here you have like n electron in the quantum dot, here n plus 1, and if you continue, it's so on and so forth.
It looks like you are considering a very weak coupling between the source and the carbon nanotube, right? The peaks are very narrow.
Yes. Yeah. So then, I mean, a way to model it is to consider that we're in the adiabatic model. So I mean, indeed, goes with what you say. So the tunnel, I mean, we have these two conditions. So the coupling between the quantum dot and this dissipation rate of the mechanics. I mean, we are in such conditions that we are in the adiabatic model, in which we can consider that when the energy level of the quantum dot is here, then its population is 1. When it's in the middle, it's 1/2, and when it's above here, it is 0. And we consider that it doesn't take like a significant amount of time when we vary the potential to change from one state to the other when we shift the position. So I mean, using this model, what we have is that basically the equation of motion of the carbon nanotube can be written in this way, in which you see that it's like a very typical equation of motion for like an oscillating system, but you have the dependence on the average population of the quantum dot, the quantum dot. And so depending on the population, you will have a change in the rest position of your oscillator. So yes, basically, if you change population, you change in rest position, and then you change in the oscillation period. So that is a way to see the coupling between the quantum dot and the carbon nanotube. So now, what can we do? I mean, thermodynamically with this mechanism. What is nice is that, you see, if we have our quantum dot that is here, and that we let it oscillate, so because of the mechanical motion, the energy of the quantum dot is oscillating in this region. Here, it doesn't do anything because the population of the quantum dot is 0 and it stays 0 over the population. So nothing happens in this region. Whereas if we oscillate in this region here, we will go from a population 0 to a population 1/2. And then when we go up, we go from a population 1/2 to population 0. So effectively, we can calculate like the work that is done on the quantum dot in each of the two halves of this mechanism. So when it goes up and when it goes down. And basically what happens is that when this energy level goes up, so when we go from the population 1/2 to population 0, this is equivalent to a Landauer erasure. And in this case, there is an energy flow that goes from the mechanic to the quantum dot. So here we start to see an engine getting built with this type of platform. Of course, when we do the other half of the cycle, it's the opposite. It's a Dillard engine. So in this case, we have energy that flows from the quantum dot to the mechanics. So this is nice, but as I told you, I mean, here in this case, the charge qubit is like, it's just a bit actually. It's either like, well, it's a given number of electrons in the quantum dot, but we cannot play so easily with coherences with this type of qubit. So is it possible with this type of platform to have like coherences and to see some, I mean, some thermodynamics at stake with coherences? So the answer is yes, or at least yes, maybe. But first, I want to discuss what does coherence change in thermodynamics. So there have already been very nice papers about it. This paper by Alexia and others some time ago about the work cost of keeping state with coherences. But the one I want to focus about here is this one by Kammerlander and Janet Anders that describes this mechanism. So basically the idea is that if you have a state with coherences in the energy basis, then you will be able to extract some work out of this system by erasing the coherences. So basically how it works is that you start with this state here that has some coherence in the energy basis like that. What you do is at first you rotate it here. So during this process, you indeed will give a little bit of energy to your system. But then what you do is that you will suddenly increase. So if we imagine that this is a spin, for instance, you suddenly increase the magnetic field. So this is the little part that we see here. So to have it in the, to increase the size of the arrow that you have here. And then you will, in a much longer period, decrease the magnetic field again to have the size match the size you want to end up with. And by this process, you will be able to extract some useful work. So maybe another nice way to view it is this one. So this is the representation I made because I find it easier to view it in this way. So let's say you start with this state here that has some coherences in an energy basis that would be like still around like the sigma z here in this representation. So first you do a rotation of the state. So this is easy, you do it quickly. And I mean, it just rotates states. Then what you do is you do a sudden change in the Hamiltonian. So basically a quench, in which, I mean, your state doesn't have time to evolve, but the Hamiltonian is changing. So here you will change the entropy of your system. Okay. And then what you will do is that you will do a quasi-static isothermal evolution. So this time very slowly, of course. During which this time you want that the state stays as its size, but it is the Hamiltonian that you're going to change very slowly. I mean, the whole purpose of these two steps is really to go from like an arrow that is in a certain relation between the size of the block sphere and the size of the arrow, and you want to change this proportionality without having to, well, with the less cost possible and with extracting the more energy possible. And then the last step is just to come back to the initial Hamiltonian in such a way that you exactly find your initial state to which you have removed the coherence in the energy basis. So that is basically the protocol that was described in the paper. So that's an interesting way to see an energetic interest of coherences. So now with the setup that I described to you before, how can we have a system that has coherences? So what we can do is that this quantum dot, instead of playing with a charged quantum dot, we can play with a spin quantum dot. So, okay, I call it an effective spin qubit because actually it's a little bit more complicated. To have it, you need to have two quantum dots, each of them having an electron and a spin. And then we're not exactly sure if we're dealing with a spin or a valid qubit. But okay, let's say we have some effective qubits. And basically, we have some magnetic field in the cryostat, because all this is in the cryostat. And so the Hamiltonian of the spin that we have here, it's going to be this one, where here, I mean, this is like a 3x3 matrix. This is like the Pauli operators, and this is your magnetic field in all directions. So it's a vector, really. So now have those, because I mean, if we want to do thermodynamics, we want to use this mechanical oscillation. So how does our spin qubit interact with the mechanical oscillation? This is not trivial at all. And until now, it has never been shown how a spin qubit could interact with a mechanical oscillation on a carbon nanotube. So, I mean, this was what we wanted to go for. So here, what is interesting and what we noticed is that actually, due to the structure of the carbon nanotube, this geomagnetic ratio that you have here, so this tensor, it will be strongly anisotropic and it will strongly depend on the shape of the carbon nanotube. So effectively, it's as if like, okay, imagine that this is the carbon nanotube like that. So it's strongly bent. And you have an external magnetic field that is in this direction, let's say. But because the geomagnetic ratio is so different if you are along the direction of the carbon nanotube than if you are perpendicular to it, the effective magnetic field that you're going to see here, it is this one. And here it is this one. So you see that depending on where you are on the carbon nanotube, you're going to see a very different effective magnetic field. And what's more is that when the carbon nanotube is going to oscillate like that, it will effectively, change the angle of the carbon nanotube near your quantum dot, and then it will change the effective magnetic field that you will see. So now we have an effective magnetic field that actually depends on the oscillation. So we have our coupling. I mean, the coupling between the spin and the carbon nanotube really comes from these mechanisms. So what does the geomagnetic tensor depend on? So as I said, it depends on the position. So this chi is basically the position of the quantum dot in this vertical axis like that. And it also depends on the gate voltage, because indeed, there are two ways to deformate the carbon nanotube. One is just via its oscillation, but the other one is also by changing the gate voltage here, I can change the shape of the carbon nanotube. So there are these two contributions. So to make things simple, what we do is that we assume that we have small deviation around the DC voltage applied here and around like the rest position of the carbon nanotube, which we call 0. So basically, this geomagnetic ratio, we are going to write it this way, with a contribution when everything is at rest, a contribution that comes from an applied voltage here that will be oscillating. So this is a drive, basically, and a contribution that depends on the position, so on the oscillation, and a last contribution that depends on this oscillation, but at second order. So a nice way to write things is to consider what happens when we have no drive and no oscillations. So basically, in this expression here, I say V AC is 0, and I have no oscillation. So my carbon nanotube is at rest. So I only have this part of the geomagnetic ratio. So this will help me to define the quantization axis. So basically, in this, if I just use the G0 in this expression, it will simplify things a lot. I can write things in this way. And then this sigma tree is what I define as the quantization axis. So basically, when everything is at rest, the energy of the spin is along this direction. Okay. Now, when I have some drive, I still have no oscillation, but I have some drive. So the contribution of the drive itself is going to come from this term here. So it's going to couple. And what we observe experimentally is that, of course, the drive is changing the state of our spin. So it's inducing a rotation. So this is why we add like this term here with a sigma 1, which then is rotating the state of the spin along the sigma tree, which is an effective sigma z. But here, we define it this way because it's a convention for the quantization axis, because it doesn't have to be the same as the sigma z that are here. Okay, so now we have like the Hamiltonian for the driven system. So yes, the effect of the drive on the spin. But now we needed to add some modeling of the mechanics, because we noticed that the mechanics were not just easily responding to the signal we sent it. So basically, the mechanics behaves this way. So it has an amplitude. So this is the amplitude response of the oscillator driven at some frequency. And so it oscillates like that. So there is this cosine. This is the frequency at which we drive the mechanical oscillation. And then this is the phase response to this driving. So here what we noticed looking at the experiment is that the mechanical response, it looks very similar to a nonlinear damping oscillator. So this is the fit that you can see here. So in black, you have the damping response fit, so the theoretical part. And in orange, you have what is measured experimentally. So you see that it seems indeed to be strongly nonlinear behavior for the mechanics itself. So putting everything of this together, what we have is that we can write the total Hamiltonian, which will be the spin driven plus the contribution of the mechanics. Yes.
Can you show the plot again?
Yes.
I'm just wondering the path of this steep rise, is that just the non-linear?
Yes. Yes, if it were linear, it should be symmetric with respect to the driving frequency. But here, because we have this non-linearity, this is what we have this sharp thing like that on the edge.
What's
Okay.
the frequency?
But the frequency, I mean, it's about 300 megahertz. It's basically an hysteretic effect. I mean, I have not this even in my backup slides, but basically you have like a shape, and when you go from one direction, you will, I mean, the frequency is going to evolve in a certain way. And when you come from another direction, the frequency is going to evolve in a different way. And this is why here, going from there, you have like this sharp shift like that. But yes, this is due to the nonlinear damping model. Indeed. So now we can write the total Hamiltonian for the spin. So it will be so the bare Hamiltonian of the spin plus the drive plus the contribution of the mechanics. So here we write only the contribution at second order because we noticed that this is the one that gives us the best match with the experimental data. So this is an experimental plot of the frequency with respect to the magnetic field along the direction of the carbon nanotube. So here you see that, I mean, there is like some, the frequency like that, but when you get close to the mechanical frequency, the frequency of your qubit, it starts to bend. And this is exactly what we find with our theoretical model. Because basically adding this term in the Hamiltonian, you see it's a term in sigma 3 also. So we can add it with the bare Hamiltonian of the qubit, well, of the spin qubit. And then these two together, if you replace this by its the model of the nonlinear damping oscillator, then it tells you that we have some effective qubit frequency, which can be written this way. And this is exactly what appears here. So this is basically, I mean, the main result of this paper that should appear soon about coupling an electron spin to the mechanical motion of a carbon nanotube. Okay, so, oh no, wait, I have a conclusion slide, yes. So, I mean, basically the main messages here are that I showed you that we managed to see a first realization of a spin mechanical coupling on a fully suspended carbon nanotube. So this is the first time this has been seen. I mean, there were already some coupling between the spin of an NV center with a mechanical motion, but never with a carbon nanotube. So that's an interesting result in this respect. So why is it interesting to couple the two? Well, I mean, this could have application for classical and quantum information processing, also for sensing, as well as long distance spin-spin coupling, because if you imagine that you have a spin in this carbon nanotube that's coupled to the mechanical motion, that you have another spin that coupled to the same mechanical motion, for instance, you will be then having like a mediated spin-spin coupling here. And then you can also investigate motion at the quantum limit, which is this type of platform. And now what we're trying to do, I mean, the next step of this project basically is to use this spin mechanical coupling to build the protocol I showed you to try to extract work from coherences. So there are many tricky parts about this because it's not exactly clear what is our bus, what is the temperature of the bus, and we need to have this information to do the quasi-static step. But I mean, we're working on this, and we hope to be able to perform this protocol and to see in the mechanical oscillation, I mean, the work that we will have extracted from the spin due to its lots of coherences in the energy basis. So that's our next goal on this project. So if you have questions before I move to the second part, which is quite different. So yes.
Can you show the plot just before it's like the frequency was
This one?
yeah, is that on the left, the experimental plot? Are you seeing some sort of periodic structure there?
Here like that. I mean, this and this.
Yeah.
Yes, it does appear, but for the moment, we're not exactly sure what this is. I mean, this could be that it's not really a spinning qubit. It has effectively many more levels because it's not even really I mean, it's a spin valley qubit, so it has effectively a lot of energy levels, and this could be what we see here, but I'm not 100% sure. Yeah.
Is there a reason why you need to go to second order in the mechanical displacement, but only first order at the time?
Well, I mean, the reason why we have to go to second order for the mechanical displacement is that we want to see the shift here that is only on one side. So we notice in the experimental data that we have a shift that is going only in one direction, and this we cannot have if we have just first order. This will just broaden the thing and not have like just a single direction. For the drive, I mean, for the drive, it seems, I don't know, it seems enough to just go to like the first order. I mean, it seems to match well the results, and I mean, I don't see why we should go to second order with the drive, because it's just like we apply just some oscillating potential. It's driving the qubit, so it's a very typical way of modeling like a driven qubit by a drive. We usually but for the mechanics, it's because we see this picture of like this. I mean, it's not symmetrical, so yes.
How you treat the two?
No, but that's a great question.
Yeah, I have a comment. I think it's very important that you get this term, because you can make cap states, for example, in the mechanical oscillator.
Yeah.
You get outside the linear regime of the oscillator. So this is typically very hard in mechanical oscillators, and if you have it here, it could be very nice.
Yes. I don't think we comment so much on it, but it's I will look more into that, yes. Because it could be a good motivation. Okay.
I think you also mentioned applications with sensing. So I was curious perhaps to say, and then you said, so you want to make a sensor out of it. So for example, with carbon nanotubes, I also by looking at the resonance frequency, you can set up the NAS, for example. So in this case, are you sensitive to like the spin way?
Well, the spin, yes, but I mean, maybe this could be useful as a sensor for like local magnetic field, because here we have this external magnetic field, and this is one of the coefficients that will appear in the equation, and the system is pretty small itself. It's just a quantum dot and like a nanometric size carbon nanotube. So I think that probably in order to like measure very locally magnetic field, this could be like nice sensing application. And I know that there are some work in this direction. I mean, people are working in like measuring precisely local magnetic fields. Maybe a bit okay, so now I will move to a very different topic, which is much closer to what we've been discussing together so far, about the nature of measurement-induced energy exchanges. So, okay, I will go fast on this slide because it has been said already a lot. But basically, yes, the question is, we know that when we measure a system that, when we measure an observable that doesn't commute with the system Hamiltonian, then we can have energy exchange with the system on average even. So here I'm not going to focus on like the post-measurement part as considered just before, but really on average quantities. So I mean, this average energy change of the system has been called I mean, average quantum heat. I prefer to put average here. And what I'm going to try to answer here is where does it come from and what is its nature? So by nature, I mean, is it heat? Is it work? I mean, how can we define it? Using the models that Alexia and many others have already described. So to do this, I'm going to focus on the pre-measurement part. So as we've been discussing before, I mean, the pre-measurement is going to be basically our system interacting with a meter system, which will result in the end if we trace the state of the meter on a non-selective measurement on the system we're looking at. Of course, to finish like the total measurement, we should add this collapse, which is going to go from this non-selective measurements to indeed the selective measurement. So, as I said before, this idea is due to Neumann. So let me first give you an example. So this is inspired by this 2-qubit engine paper that we've been talking a little bit about before. But here, just to simplify things a bit, instead of having the 2 qubits, I just have 1 qubit, but whose their Hamiltonian is tilted. And I'm trying to measure its state in this sigma z basis using another qubit. So the total Hamiltonian will look like this. So here what's interesting is that I consider that the meter qubit, its energy level are degenerate, so I don't have like an HM, so I don't have a bare Hamiltonian for the meter qubit. So our total Hamiltonian is this one. So what happened in this case? So basically we have here the Hamiltonian of the system. Here we have the interaction part of the Hamiltonian. And ideally, what we would like to have is that if the system is initially in some superposition between excited and ground, and that the meter itself is in the ground state, then the state of the meter should evolve according to the state of the system to extract the useful information. So in this way, so the effect this will have on the system is basically that it's going to project its state on this measurement basis. So what we observe when we look at the different contribution of the total Hamiltonian, and we look at the average quantity, when we during this pre-measurement, what we observe is that so during the pre-measurement, we have only a unitary evolution. So of course, the total Hamiltonian is constant here. What we have is that the Hamiltonian of the system is increasing because basically we're measuring in this basis here. So you see, if this was its energy because the bare Hamiltonian of the system was tilted. So this was like the energy of the system before it was there, after the measurement is here. So we are increasing the energy of the system like that. And here you see that to compensate, what we have is that we have an equal and opposite decrease of the interaction part of the Hamiltonian. Then, I mean, this pink part is just like included already in this one, so you don't have to care so much about it. And then when we do like the measurement, what happens is that we're giving this amount of energy to the system, and as you can see, this amount of energy is exactly the one that we will at the end need to give in order to turn off the interaction between the meter and the system. So already we can answer partly to the first question I said I will answer, which is the energy given to the system is actually the energy necessary to turn off the interaction between the system and the meter. So now, if we try to generalize this a bit more, because here it was just an example, we can have the following model. So very standard. So I think you understand each of the terms here. So it is important to mention that at the beginning, the interaction between the system and the meter is 0, so they're not interacting. And at the end also, we want that they're not interacting anymore. So we finish the measurement at the end. So basically, the quantum heat is the change of energy of the system on average. And because we're making the assumption that this HM, it commutes with the total Hamiltonian, then it's not going to change its average energy. So, I mean, we know that the average energy is not going to come from zero. So then what we have is that the change of energy in total is equal only to this part because this is 0 at the beginning and the end, and the change of the meter energy is 0 by assumption. And this is equal to the work done, during this time-dependent evolution, which is just the integral of the part that is time-dependent indeed, because we vary, this is the only term that varies in time. So here,
Can I ask just a simple question here? There's a dimensionality issue here. So you've got a voltage times the, or an energy times the time.
yeah, I should probably divide. Oh no, it should be the derivative of that. I see. Yes, it should be the derivative.
Derivative of
Yeah, yeah.
expectation.
I forgot the dot, yes.
Gotcha.
And so basically, here the message is similar as before, but it's more general, is that the energy done on the system is the energy necessary to modulate this time, because here we don't even assume that it's just turn on and then turn off. Here it could be like a smooth modulation. So it is the energy necessary to modulate the strength of the interaction. So then what is the nature of this energy? Is this heat or is this work? So as said before, there are arguments on both sides. So we could say it's heat because the measurement induced stochastic energy exchanges. And also because the entropy of the system changes. And because correlations are getting built between the system and the meter. So this all goes together, of course, but this is a strong argument to qualify this as heat. But also we could say that it's work because dynamic during the pre-measurement is unitary. And also because what I find here that the energy given by the measurement is that of turning on and off the interaction. And turning on and off is just like a time-dependent turning on and off. It's a classical thing that an operator can do. It seems very much like work. So in order to answer to this question, I'll use this bipartite quantum energetic model that has been described already. So in which basically the idea is to decompose the total state in this way. So with a correlation part and a part that is separable. And then to define very simply the energy of each of the system just by this, just by the bare Hamiltonian of the system and its state. Then what we do is that we define the work as the energy that comes from the uncorrelated part. So you see, we only have this part here in the definition of the work. So it is a change of energy that will preserve the entropy of the subsystems. And the definition is exactly symmetrical for the blue part. And for the heat, it comes from the correlated part. So here you see, it is exactly the same expression, but instead of this uncorrelated part, we have the correlation here. So basically, we can summarize this in this table, which is maybe a long equation, but at the same time, it's nice to have the broad picture, in which you see that basically the change of energy of of each system is made of the change of the work flux, the heat flux, and some external work done on the system. So until here, we haven't discussed about this external work done on the system because most people who presented this model didn't have a time dependence in the Hamiltonian. So this part here only comes because here I have a more general model in which I have this time dependence. So, the advantage of this model is that it's fully symmetrical. So you see, the whole and B are, on A and B are fully exchangeable. It's fine. It doesn't rely on temperature and system size. It doesn't depend on, we don't assume anything about the initial state of the system or coupling strength. So it's very agnostic as much as we can. So what if we apply now this framework to the case of the measurement? So you see, it simplifies things a lot because already I have only a time dependence on the last term here. So this is automatically 0, this is automatically 0. Then I assume that this HM, it commutes with the entire Hamiltonian. So basically there is no change of energy of the meter. So this is all 0. So what we get here is that the energy received by the system measured, it has both a heat and a work contribution. And it is mediated by the interaction energy. So where does this heat and work that are performed on the system come from? They come from the change of the interaction energy. And where does this change of interaction energy come from? Well, of course, ultimately from the modulation that is done by this time-dependent Hamiltonian. So if we come back to this example of the treated qubits, here things are very simple because we are in the case in which the average value of the sigma x is 0, because we start with an initial state that is this ground state. So what is good is that thanks to this, the change of energy of the system is only going to come in the form of heat. So it's nice. Now we can answer the question. In the case of measuring this tilted qubit, so during this pre-measurement, the energy comes from the modulation of the interaction, and it is of a heat nature. Here, in this case, it's easy, we can say it clearly. Now, if we take this example, we can go a little bit further. So here, it's my last example, and it's the case of measuring a tilted qubit, but this time not with another qubit, with a cavity field. So this is why here you see the Hamiltonian of the field, and the interaction is of this type. So now what happens is that due to this interaction, if we start with a coherent state in the cavity, this coherent state, it will get a positive or a negative phase depending on the state of the qubit in the measurement basis, of course. And then to quantify how good our measurement is, we can look at the overlap between the two final states of the field. So here, making the assumption that we turn on and off the interaction between the cavity and the qubit sharply like that, and that at maximum it's equal to this chi value. So I'm sorry, before chi was the oscillation position, now it's the value, it's the strength of the measurements, but I saw this too late. So using this definition for the work done on the system, we can simplify things a bit and have this final expression. So what is nice is that we can start to see conditions for which we will have zero work. So condition for which indeed we will have that the energy done of the system is quantum heat. So it's really heat in the definition of bipartite quantum energetic that we've been showing so far. So what are the conditions for this to be heat? For quantum heat to indeed be heat. So we have to have this to be equal to 0. So basically, how do we have this equal to 0? Well, I mean, this is that there is the duration of the pre-measurement here. There is also the average of this OM, so the average value of the operator of the measurement apparatus. So we saw that in the case of the qubit, it was 0, but it's not always the case. For instance, in the case of the cavity field meter, this is not 0 if we don't have like a trivial field. And then we have here what is going to become just the derivative of the average value of the observator we're trying to measure at the time of the measurement. So now we want to see, is it possible to have a measurement that has 3 conditions? We want to see, is it compatible to have a measurement which is instantaneous, that is heat-only exchange, and that is faithful. So faithful here, we mean that the overlap between the final states of the meter is 0. So is it possible to have this? Well, what we noticed is that it is possible, but for this you need very specific conditions. Because in order to have a faithful measurement, what you will need is that the average value of OM, which is actually the average number of photons, because OM was A dagger A. So this should go to infinity, because indeed you want this part here to go to infinity, but still you don't want this to go to 0. So this is why you have this condition here. So these are the 2 conditions to have a faithful measurement. In order to have like the bipartite heat only, then you need to have this part that goes to 0, which is the term that you have here. And in order to have an instantaneous measurement, it's simple, just tau going to 0. So now if you try to look at all these conditions, you see that they're not always compatible. It's possible to have these 2 compatible here, but then if you have these 2 compatible and that you don't have this, you cannot have bipartite heat only. So it's nice because we see that depending on what we want, we can place ourselves in different conditions, and not all measurements are going to do the same. So if we choose a meter, for instance, who has like the average value of OM, which is equal to 0, then it's nice. We can have like bipartite heat only, a faithful measurement, and instantaneous measurement. So in this case, indeed, quantum heat, like average quantum heat, is heat in the sense of a bipartite quantum energetics. So basically, to conclude, I mean, the message is the following, that in the bipartite quantum energetic framework, the pre-measurement leads to heat-only exchange if the system well being instantaneous. Well, so if we have this precondition, we can have this precondition only if the average value of O of M is 0, or if the derivative of it should be S here, of OS at the time of the measurement is 0. Well, this is interesting because it means that we should measure the system at a good time, because indeed, O of S is a quantity that doesn't commute with HS. So if we don't touch the system, if we don't interact with it, its bare Hamiltonian is just HS. So the average value of O of S is going to evolve in time. It's going to oscillate. So basically what it tells us is that depending when we measure this OS, we will have only heat or only work or a mix between the two, depending on when we will measure our system due to this equation. And this is basically the message here. If you have any questions.
Yes.
So you're